Hello everyone, I am Zach Peterson. Welcome back to my channel where I answer all of your questions about PCB design. Today in this video, I'm going to be going over how to fan out high density BGAs and specifically how to work with a 0.4 millimeter pitch BGA package. Now I received a really great viewer question on my LinkedIn, and of course, if anyone out there watching asks a great question, it just might end up in one of these videos. So let's go ahead and jump on the whiteboard first. We're gonna do a little bit of a review about BGA pitch and how that impacts via placement as part of your fan out strategy. And then we will look at how to do via in pad in Altium and how to work with a 0.4 millimeter pitch BGA. Let's go ahead and get started. Now, before we jump onto the whiteboard, let's take a look at that viewer question. Vishnu Rajan writes, "Hi sir, I have a few doubts in Altium. I have 6.6 mils as the air gap between BGA pins. How do I fan out a 0.4 millimeter BGA? I tried to do this with blind vias with 4 mil diameter and 8 mil pad." Well, from reading your question, Vishnu, it sounds like you attempted to use one of the automated tools in Altium to fan out the BGA, and it didn't work. And unfortunately, without looking at your design rules or looking at your design file, I can't really say why that was the case. However, I can say that you are on the right track using a 4 mil blind via to fan out a BGA with that pitch. And we'll see why that is the case when we look on the whiteboard here in just a moment. Now, I will say that at a 0.8 millimeter pitch or a 0.4 millimeter pitch, the approach for doing the fan out is very different, and Altium's tools will automatically fill in fan outs with different styles. At the larger 1 millimeter or 0.8 millimeter pitch, the fan out style is going to default to dog bone fan out, where the vias are off of the pads. And then at a tighter pitch, like 0.4 millimeters, the only fan out that you can do is with via in pad. So your tool may have failed because you didn't have the via in pad rule enabled. Now that's a little bit of an aside. So first, let's just go ahead and take a look at the whiteboard. We're going to see what the limits are for placing large and small vias in a BGA footprint in order to do dog bone fan out and via in pad fan out. So before we look at how to fan out a BGA with pitch as small as 0.4 millimeters, let's briefly look at the typical fan out approach, which is a dog bone fan out. Normally, we would have an array of, for example, 4 pads like this in our BGA footprint. And these pads would then have a via hit right here in the center, and then you would have the pad for the via like this. And then one of these pads is going to route to this via using a trace, and that basically completes one part of the dog bone fan out. And this basically repeats across the whole BGA footprint for all of the inner rows and columns. So at what point can you no longer do this? Well, let's just use an example here of a typical BGA footprint where we have, for example, 0.8 millimeter pitch. Now with a 0.8 millimeter pitch, that's 0.8 millimeters between the centers of these pads. And at a 0.8 millimeter pitch, the ball size on the bottom of the package is probably going to be such that the pad diameter here is probably 0.45 millimeters. Again, just as an example. So with a 0.45 millimeter pad, how large of a via can I place here in the center and still accomplish a dog bone fan out without violating any of these clearance restrictions between the via pad and the BGA pad? Now that clearance between the via pad and the BGA pad is going to be my limiting factor that determines when I can no longer place a via in the center of this pad array. And when that happens, I'm going to have to move that via into my BGA pad. So that size for this via you will find for a 10 mil via with a 20 mil diameter pad will give you about a 4 mil clearance right here between this pad edge and this pad edge. That's getting right up to the limit of what most fabrication houses can reliably do. Now, if you were to size this up a little bit bigger, for example, for class 3, and you did a 10 mil via diameter and 22 mil pad, Now you'd get this down to only 3 mils of clearance. So that's really getting to the edge of the fabrication capabilities. Now, as you can see, these are typical values for a mechanically drilled via, but once we place one of these vias into this footprint for a 0.8 millimeter pitch BGA, we pretty quickly run up to the clearance limit that we're allowed between these pad edges. So that's the point at where we're now going to need to either make this via smaller, or we're going to have to move this via back into the pad. Now with the 0.8 millimeter pitch BGA, we could of course make this smaller and still mechanically drill it as a through hole. For example, we could go down to 8 mils, and then we could make this pad size, for example, 18 mils. And then that's going to increase the distance between this pad edge and this pad edge basically to 5 mils, okay? So there are some tricks you can play as you start to make these vias smaller, and that's going to allow you to access smaller and smaller packages. But again, at some point, you're going to be forced to move this via into the center of this pad. Now, when that happens, we're typically at a 0.5 millimeter pitch. Well, what about a 0.4 millimeter pitch BGA? Well, in that case, we're going to have a via that we have our drill hit centered right here, and the via diameter is going to have to be small. It could be anything from, for example, 4 through 6 mils, although typically it's about 4 mils. And then we're going to have a pad around that via that basically sits like this, and then it could be oversized compared to the BGA pad. Okay, so we need to have enough annular ring on here in order to ensure that we have sufficient copper after we drill this hole in the BGA footprint, so that way when we have a trace attached onto this pad, we don't sever that trace. So there needs to be enough of a pad oversize. But the exact size of this pad oversize that you have here on this via is going to depend on whether this is mechanically drilled or laser drilled, because mechanical drilling and laser drilling have slightly different positional tolerances. So laser drilling is going to be much more precise. And when you're down here at this 4 mil drill diameter for this via, you're going to be much more precise, and you can generally use a smaller pad size on these pads for these vias. Now, when we have this via in pad like this, we can then route, for example, on an inner layer shown in green, basically like this vertically, and we can route underneath one of the pads above it. Now, what is going to be difficult to do with some of these pads on the same layer is to do this style of routing where we route between these pads. And that's because it's going to force you to get this trace width to be pretty narrow. And it could be narrower than the etching limit that your fabricator allows. So you need to check on your fabricator's capabilities and then figure out what width you need, and then measure these clearances to ensure that you can fit this trace between these pads before you actually do these routings. Otherwise, you're going to have to put a via here, transition into the inner layer like we have here, and then route up vertically instead of routing in between these pads. So to see how to do this, what we're going to do now is take a look at an example inside of Altium Designer. We're going to see what via sizes we can use in each of these pads, and then we'll be able to see if we can actually fit a trace like this in between these pads on the same layer. So now let's take a look at a 0.4 millimeter pitch BGA in Altium Designer, and we'll see how we have to approach this fan out. So here you can see I have a component with a BGA footprint. You can see here if I just do a quick measurement of the distance between the pads, it is a 0.4 millimeter pitch BGA. And we want to see how we can approach the fan out for this component. You can see here on screen, I've assigned all the pads to the same net just for convenience. And what we're going to do is we're going to start to put some of the vias in pad and start those via transitions into the inner layer so we can fully fan out this component. Now, the first thing I want to do is take a look at the layer stack. So if I just bring up the layer stack manager, you're able to see that this is a 6-layer board. We're using 3 mil outer layers. The total thickness is standard thickness. It's 61 mils. You can see here that the outer layers are separated from the core by 3mm dielectrics, and the reason we need those 3mm dielectrics is because we are going to be using small diameter microvias in order to reach the inner layers from that 0.4mm BGA. Now we need to do this because, as we're about to see, this is the only way you can get into the inner layers from that BGA footprint. So you can see here how I have my microvias set up. We have 2 buildup layers on the outside of the design, each with a microvia transition. Here we have a blind microvia and a buried microvia, and we can stack these in order to reach the inner layers. Now we could have a through via right here in the core if we wanted to. I can go ahead and add that now and just set that as a layer 3 to layer 4 transition. That would technically allow us to stack all the way through the entire stack up, but we really don't need it in this particular design, and we'll see why that's the case in just a moment. So let's go ahead and go back into the PCB. Now, if I zoom out for just a moment, you'll see here that I've created a few vias that we can use to complete this fan out. Now here I have a through hole via, and you can see here what the hole size is. The hole size is 10 mils, and then the pad size is 20 mils. And it should be pretty clear that basically no matter where I put this, it's not going to be able to be used for fan out routing. Of course, here, if I put it on one of these pads, you can see that I'm getting pretty much right to the edge of what I can consider valid for clearance in this design. In fact, if I go ahead and just turn off my snap, and then measure from this pad edge to this pad edge, you can see we get about 2 mils of distance. So that 2 mil clearance is already going to be pretty aggressive in terms of what most fabrication houses can etch. And of course, I would never be able to put 2 of these vias right next to each other and fully fan out these inner rows using these through-hole vias. So these through-hole vias are already out. We can't use them. So we're going to have to use these smaller microvias, as you can see here. So here I've set up microvias with 4 mil hole size, and this matches the diameter that was stated in the viewer question. Here I'm using a 10 mil diameter pad, but we could just as easily set this to 8 mils. So I'm going to leave it at 10 mils for now. So if we're going to use this via to fan out this BGA, we just need to decide which pins does this via need to be placed on. Now, in order to do that, we have to look at where we can route traces in this BGA. Now, if we start to route, for example, from row 2 outside of the BGA using a standard trace width, you're going to see here that this requires also a very small clearance between the edge of the trace and the edge of these pads. Now, I could make this trace width as small as, let's say, 3 mils. And then again, if I turn off my snap options and just do a quick measurement, we can see what the clearance is. This clearance comes out to, again, 2.621 mils. A 2.621 mil clearance is going to be too small for a lot of fabricators to handle with any level of reliability. And so that basically eliminates routing these traces like this unless you can get them even smaller, for example, down to a 2 mil width. Now, if you can fabricate down to a 2 mil width, you could route between these pads, and you'll see here that this leaves just about 3 mils of clearance between the trace edge and the pad edge. So that could be feasible, but again, you have to check with your fabricator that they can etch traces down to 2 mils with 3 mil clearance. Now let's just assume for a moment that we're not able to route these traces in between these pads like I just showed. How are we going to handle this fan out? Well, what we would then do is we would basically first place our vias along the outer row. And the reason we're doing this is because that first set of traces is going to route straight into these pads on the top layer. Then we're going to have to route our traces into this set of pads on the very next layer. And you can see I've placed all of these pads along this first row just by copying and pasting. Now here, I can then take this set of vias, I can copy them, and I can copy them to all of these other rows, and that's going to fill in all of these inner rows with that fan out. Now you can do this in an automated way in Altium Designer, but again, I'm just showing you a quick way with copying and pasting onto selected pads. Now you can see here we've already filled up all of these rows with all of these vias. And that's going to allow us to then access layer 2, with this set of vias. So now that I'm on layer 2, I can then just route straight out from these traces, as you can see here on screen. Now, what about layer 3? What about this next set of vias? Well, with layer 3, I would then want to copy this next microvia onto all of the next set of rows. So here, I'm going to copy my transition from layer 2 to layer 3 and just paste it along this row of vias. And so now this row of vias is set to reach layer 3, as you can see right here. And we can then copy this set of vias onto each of the following rows. And then you can see here, layer 3 is fully accessible, just as I show here on screen. So now on layer 3, we can then go ahead and route these traces straight out, just like you see here on screen. So now we've handled most of the vias in this BGA package, but what about this last set of 8 vias? How are we going to get traces to come into these vias? One thing I think that everyone needs to know about BGA packages is that this central row of pads tends to actually be power and ground. So you may not need to route traces into all of these pads. What you may actually need to do is connect these pads to a plane. And in order to do that, you don't necessarily need all of these microvias coming into this central set of pads. What you could actually do is then use those through holes, and you could place those through holes, for example, here in between these pads. So just by placing the through holes like this, I can then touch all of these pads using these 2 through hole vias. I can then fill in any of this space with, for example, a polygon. And by then drawing in this polygon, I've basically created a bridge between all of these different pads, assuming that they're all power or ground. Now, connecting them all to a plane like this, again, you do want to make sure that you do provide a nice low impedance connection between these pads and your via. So that means you may need to draw some copper in here in order to fill in that empty space. And that's essentially it. We've basically completed the fan out for this 0.4 millimeter pitch BGA. So again, let's review. We were unable to route traces in between these pads, and so we were forced to then use via in pad in order to get signals into this first row of pins on the BGA. And in order to do that, we used microvias that allow us to then route in on layer 2. Now, what about the next layer? Well, now we can then route in on layer 3 using another set of microvias. And then finally, the inner set of pads were assumed to be power and ground. We're able to connect all of those in a group to a plane layer using some through-hole vias. Now, another thing I'd like to point out here is that in many cases, you are not actually routing any of these traces coming into this BGA package on adjacent layers. You might actually separate them with a ground plane, especially with this being a digital processor. So you would actually fill in some ground in between these layers. But guess what? The principles that we've shown here apply and extend really to any number of layers and any BGA with any number of pins. So if you need to separate your signal layers with ground, that's pretty easy. You just add in another microvia transition, assign the relevant pins to ground, and then when you start to add in those microvias in your layout, they'll automatically connect to that ground plane once you place it in the Stackup. That's going to provide the separation that you need between your signal layers, and that will prevent layer-to-layer crosstalk. Thanks for watching this video, everybody, and of course, thank you for all of the great questions that you send me on LinkedIn and all of the great questions and comments here on YouTube. And again, if you ask a great question, it just might end up in one of these videos. Make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of my content on this channel. And of course, go subscribe to Altium Academy, where you can see all of my other PCB design videos. I'll see you next time, everybody.